All right, section 3.2, linear functions. Now you can kind of probably guess what linear means. And so what do you think a linear function is? Well, it's a function that makes a line. So a linear function, what are we going to do? Well, here's what we're going to do. We are going to identify linear functions using graphs, tables, and equations. We are also going to graph linear functions using discrete and continuous data. And we're also going to write them in real-life problems to fit the data that we give. So here we go. Let's start with our first key concept. A linear function in two variables, x and y, is an equation that can be written in the form y equals mx plus b. Now, what kind of form is that in? This is a review from last year. Y equals mx plus b, slope-intercept form, where m and b are constants. The graph of the linear equation is a line. Likewise, a linear function is a function whose graph is a non-vertical line. That's important. It's a non-vertical line. A linear function has a constant rate of change, which is your slope. Constant rate of change is your slope. That can be represented by a linear equation in two variables. A nonlinear function does not have a constant rate of change. You may remember this. Y equals kx. Whoops. Kx would be the constant of proportionality. Remember that a linear function, which is your slope, is a constant rate of change. If the constant rate of change is not constant, then it's not a linear function. Therefore, the graph would not be a line. Now, once again, in example 1, we not only have to do the problem, we must also explain. Make sure we always explain. Does the graph represent a linear or nonlinear function? This is really easy. It's not. The reason it's not a line, because it's nonlinear. So, it's nonlinear, so we write nonlinear. And the reason would be because it's not a line. Easy. B is a line, therefore, it's linear. So we'll get the easy part out of the way. Now in example 2, we could graph these ordered pairs. We could graph the ordered pairs. Now, if we don't, then we have to look at the tables. Here's what we need to know. Remember, I can't express how important it is that you remember this. M, which is the constant rate of change, is your slope. Remember, slope is your change in y divided by your change in x. So we look at A, the change in y. Let's see, it drops by 6, drops by 6, drops by 6. Your change in x goes up by 3, increases by 3, increases by 3. That means as the x increases by 3, y decreases by 6. Therefore, if you actually did this for every value, your slope is -3 for every -3. Let's try that again. Change in y divided by change in x. That would be -6 divided by 3, which gives us -2. Therefore, this one is linear, and the reason is because it has a constant rate of change. That's your reason. Now in B, this increases by 7, this increases by 11, this increases by 15. Now your x each time does increase by 2. But we do not have a constant rate of change. Therefore, this is nonlinear. So what would your reasoning be? It's nonlinear because the rate of change is not constant. All right, in example 3, tell me which of the following equations represent linear functions. So I'm just going to number them. This is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. We have 6 functions. I want to know which ones are linear. Now remember, linear functions can be written in the form y equals mx plus b. So number 1, can I do that? Well, let's see. Y equals, well, there's no x, so I could do 0x plus 3.8. Yep, so that works. You can't have square roots. That's just the first rule. Can't have square roots. You can't have x as an exponent. So right here, you'll notice that the x is a power, and that can't be right. You also can't divide by x. Let's see the next one. Y equals, I could distribute 6x minus 6. That works. And the last one, you have a power of 2. You can't have any exponents higher than 1. So therefore, y equals 3 and 8/10, and y equals 6 multiplied by the difference of 1 and x, or x and 1, are your two functions that are linear. So your concept summary so far. Representations of functions. If I said an output is 3 more than its input, remember output is kind of like y, and x would be input. An output, y, is equals 3 more than x, x plus 3. Piece of cake. Now, in this problem, here's an input-output table, sometimes called a t-table, a mapping diagram, and if we graphed it, would look like this. Now, last year in 6th grade, you graphed. You graphed a lot, actually. So, graphing linear functions. Notice that we're calling them functions now instead of equations. A solution of a linear equation in 2 variables is an ordered pair xy that makes the equation true. Every ordered pair that makes the equation true is on the line. The graph of a linear equation in 2 variables is all of the points, xy, in a coordinate plane that represents all solutions of the equation. Make note of that. Sometimes, this is, I think, new to you, sometimes the points are distinct, and sometimes they are continuous, which means they are connected, which leads into our discrete and continuous domains. Now, I believe we talked about discrete and continuous last year. Domains we have not. A discrete domain is a set of input values that consists of only certain numbers in an interval. So for example, discrete would be the integers from 1 to 5. That would only be 1, 2, 3, 4, and 5. Continuous is a set of input values that consist of all numbers in an interval. So you can't possibly list them all. So you would say all numbers from 1 to 5. All numbers, not integers. So all numbers means fractions as well. 1, 2, 3, 4, 5, and all of the numbers between them. So, if we are graphing discrete data, this is important because it will matter how you graph this. The linear function y equals $15.95 x represents the cost y in dollars of x tickets for a museum. Each customer can buy a maximum of 4 tickets. Now, this is easy. This is really easy to graph. Now, the domain, A. Think about, this is where you just got to use your brain. You got to think about it. Your domain. How many tickets could you buy? Well, since you can't buy part of a ticket, only a certain number of tickets, you only can buy a whole number of tickets. So you could buy 0 tickets, 1 ticket, 2 ticket, 3 tickets, and 4 tickets. Because the 4th ticket is the highest we can buy. So this would be discrete, and you would explain that because we just explained it. I mean, it has to be discrete because you only can buy a whole number of tickets. B. Now, if you graphed it, that's easy. 0, 1, 2, 3, 4, you would plug those in. 0 tickets obviously would give you $0. 1 ticket would give you $15.95, and so on. You would not connect the lines. You would label, and we would only have those 4 points, or 5 points. Here's a study tip for you. The domain of a function depends on the real-life context of the function, not just the equation. So you can't just look at the equation and be like, oh, this is what it means. The domain determines on the real-life context of the problem. Now, in example 5, a cereal bar contains 130 calories. The number C of calories consumed is a function of the number B of bars eaten. Does this represent a linear function? Now, in part A, yes, it would. So in part A, you would say, yes, it is linear. The reason is the rate of change is constant. It's never going to change. B, find the domain. Well, okay, here's what we got to know. The domain. Domain is the number of bars eaten. So B is your independent variable. That means that B represents your input. The number of calories depends on the number of bars. Therefore, B, number of bars eaten, can be any value. Could you have 1 bar? Yes. Could you have 0 bars? Yes. Could you have negative something bars? No. So we know it has to be 0 and bigger. The problem is that you could eat half a bar or 3 1/4 bar. You don't need to eat an entire bar at one time. So therefore, it's not just whole numbers, it's any number that is greater than B. And it would be continuous, and we just explained why. You can eat part of a bar. So it would be continuous, sorry, not continuously. So it would be continuous. And let me spell it correctly. Continuous. C, let's graph it. And here's your graph. I'm just going to zoom it up. Your graph would be labeled. Notice that 0, 0 is the smallest bar you could eat, which would be 0 calories. And it's continuous. Therefore, the line, or actually the dots, are connected to make a line. Actually, it's a ray, but this is a straight line. So in example 6, you don't need to write this down. But if you want to write a real-life function to fit the data shown below, is the domain of each function discrete or continuous? Let's start with just that. We know A would be discrete. And why? It is discrete because it is not continuous. I mean, it's pretty easy. It's discrete because, and let's actually make up a problem here. So let's see. We start at 6 and we end up at 6. We could say this. No, that wouldn't work. Let's try, I'm thinking here. One possibility is 2 people are bidding each other on 6 coins at an auction. Each coin will be purchased by one of 2 people. Because it is not possible to purchase part of a coin, the domain is discrete. So let's say 0, this person doesn't buy any coins, this person buys all 6. This person buys 1 coin, that means this person buys 5. This person buys 2 coins, this person buys 4. Since you can't have part of a coin, it's discrete. Now we know this one's going to be continuous. We could say that it snowed outside and there's 6 inches of snow on the ground. Every day that goes by, an inch melts. So what does that mean? It means that this is continuous because the amount of snow left on the ground is continuous. It continuously melts. It doesn't just go from 6 inches to 5 inches in one day.